Okay, so I'm going to go over the remainder of this current chapter. Um, forgot it's chapter uh, 4. Okay, chapter 4. So we covered moment of a force, and we learned definition. So moment of a force is force times the distance to the point about which we evaluate that moment. If we have concurrent forces, then it's convenient to evaluate about that point O the moment of the individual components. And then we learned the general definition with cross products of the vector moment of a force. Um, what is left to go over is the moment about an arbitrary axis, moment of a force about arbitrary axis, the concept of coupled moment. When you have two forces parallel, they are not overlapping. Um, Located, so what is their effect? They're located some distance. And then how we can simplify system of forces and couples or moments, and then distributed loading, common in engineering analysis, could be distributed load due to wind, air pressure, fluid pressure, or of weight spread um, over length over area or over an area. Um, okay, so to introduce the concept of moment about an axis, I'm going to go to page 142, where there is an example problem that you had to solve for. Well, yeah, it's a good example in general to introduce the idea of evaluating moments about an axis. So this problem, um, 39, 38, 39, we have a hinged door, and the door is hold open by this chain. And as you can see, the chain is slanted, or not the natural way you may think of anchoring this door. So this is in a horizontal plane, has weight, you want to hold it partially open. So you'd be interested in knowing what's the force, or the moment of this force about the line AB, which is the line of the hinges. All right. So yeah, this is section 545, moment of an axis about specific, moment of a force about specific axis. And he gives the example of a wrench like this one, L-shaped. The real one, as you can see here, to loosen or tighten the car wheel, has this distance smaller. But in any case, the effect of the force, because of this offset from the x-axis, would be a moment that is at some angle. Now, the response of the stud that we want to, or bolt that we want to loosen, would be due to the moment that's along the y-axis perpendicular to the wheel plane. All right, so that moment is going to be equal to, well, firstly, the moment about point O of this force. So it's magnitude of the force times distance. Now, if you want the component or part of the moment that's actually loosening the nut, the wheel nut, that for that we need to essentially project this moment over the y-axis. And projection happens, as you can see here, if you know that an angle theta, there will be, so let's see, the angle theta is provided here. We have a 90-degree angle between the arm of the force and the moment, which makes this angle likewise. So if you can see, the angle between MO and MY is likewise theta. So that's why this equation, the moment about y would be f times the distance dy, or it could be mo times cosine theta. Anyway, so moving forward, this can be stated in more general form by using the scalar triple product. So we evaluate the moment of a force about a point O, and then we project the moment, like I said, projected over the axis of interest. Here is the y-axis, and the unit vector associated with the y-axis is j unit vector. But in general, we can have interest to project the moment of a force about an axis of unit vector UA with all three components non-zero. Okay, so yeah, this can be done using the scalar triple product. And so we evaluate the moment about point O, the way we learn with determinant, and then you multiply, pre-multiply, as in a dot product, with the unit vector associated to the axis about which you want to evaluate the moment. And in concise form can be written this way. So you can expand this determinant about the first row, and that will give us the magnitude of the moment about the respective axis. Could be negative or positive. If it's positive, the moment will be in the direction of the unit vector. If the negative is the opposite. And if we want to state this vector about the axis A as a or the moment about the axis A, all we need to do is just multiply by the unit vector associated with the respective axes of components UAX, UAY, UAZ. Okay, so yeah, this is the equation. All right, so this is for now. One thing to remember, it's explained here in this sample problem. So if a force is intersecting, so we have here three forces, F1, 2, and 3, and a reference frame. So if a force is parallel with an axis of the coordinate system, it produces no moment about that axis. And if it intersects an axis, produces likewise no moment. So for example, F1 here, being parallel to the y-axis, does not produce a moment about y-axis, and intersecting the z-axis likewise does not produce a moment about the z-axis. So really, F1, it's inducing a moment about the x-axis. That will be a positive moment, and the magnitude of it will be 60 times 2, and again positive because it's the direction of x, or we can just say 60 times 2 times I unit vector. This other force is parallel to x-axis, so no moment about x, but it's producing a moment about the y-axis, and that's going to be a -1, 40 times 2 feet. And then it produces a moment about the z-axis, which is a -1, applying the right-hand rule. Yeah, that's going to be 40 times 2 feet, but again, -4, yeah, times k um, for the moment about the z-axis of this force F3. Okay, some sample problems, or hopefully we'll be able to do enough of them. And moving to section 4.6, here we have what is called moment of a couple. It's pretty common in practice to apply equal and opposing forces that are at a distance given, and the forces are equal and opposing, so they cancel each other if you sum forces. But because of them being offset by, well, in this case, zero point 0.4 meters, then that's going to cause a rotational effect. If I reduce the distance between the two parallel forces, in order to have the same effect, I need to magnify the or increase the magnitude of both forces. Again, this is called moment of a couple, sometimes just couple. Okay, so here's a top view, two parallel forces with a distance d, and then here it shows a perspective view of two parallel forces. And if we're to evaluate the moment of these two forces, again, they are equal. One is F, one is negative F, but they are at a distance R. And if we evaluate the moment of the two force about some point O, okay, which is stated here. So you cross RA with negative F and RB with positive F. Again, these are vectors, as boldface means vectors. We can factor F, and what's to the left of the cross product is actually going to be this vector R that connects 2 points on the lines of actions of the two parallel forces. In a scalar formulation, this ends up being, so assuming a planar system where the moment will have the direction of the z-axis multiplied by k unit vector. So the moment of the couple moment will be just the magnitude of 1/4 times this distance. Or vector formulation, going back to this equation. Again, cross product between R vector connects 2 points on the line of actions of the two forces times one of the forces. Okay, and so yeah, we looked at this, and I said there, in order to have the same effect, right? I can modify the distance between the two forces. In order to have the same couple moment, I need to increase the two forces. Again, they are equal and opposing, opposite. And here it shows a product 30 times 0.4 is the same as 40 times 0.3. Resultant couple moment. So if we have, well, firstly, it's stated in several places in this chapter. So a couple moment is a free vector. Okay, so you can move the couple moment parallel to itself. So yeah, and the effect would be the same overall upon the body. All right, so here's an example. I have this system of pipes, and I have two moments, M1 and M2, and I can find the resultant moment by just adding these as vectors. Okay, and I can, the point of summations, or where I represent the resultant moment, it does not matter. Not necessarily upon as they affect upon the body itself, but rather effect upon the environment to which is the system is connected. We'll talk more about this later, right? So again, it's a free vector, important to remember. You can show it anywhere. Its effect upon the uh, environment that is locating or supporting that body will be the same. All right, the moment of the two coupled force can be determined about any point, yes, since it's a free vector. And we can choose that point somewhere along the line of axis of one of the forces. But again, the forces that make the couple have no net effect because they are equal and opposing. Okay, so let's move forward and discuss the next section, simplification of force and couple system. So here is essentially clarifying the concept that a force is a sliding vector. So let's look at this three figures first row here. So here's a stick. Let's assume this is it's on a table. This gravity is perpendicular to the screen or to the printed page. So a force acting at the end of the stick is sensed by the hand at B, same whether it's at the end, somewhere in the middle, or close to the hand. All right, so a force is a sliding vector. Has same effect if it's shown anywhere along the line of action of the force. Now, everybody realizes that if I'm moving, so if I move the force from the end of this stick close to the hand will sense the same load, but the stick that is to the right of the force will not be loaded as it is here originally. All right. So again, I'm talking about the effect upon the environment, essentially, the support here, the hand. Now, if instead I have a force that's perpendicular to the stick, so how can I, or what will be an equivalent system? So if instead I take this force and place it at the hand, all right, in order to have so again, this force F, I move it here at the hand. In order to have the hand to sense the same type of loading, I need to introduce a moment couple that is equal to F times the distance D. All right. So yeah, this is essentially the essence of this section, and the in general. So you assume a systems of body loaded with forces and moment, and the for simplifications, we would like to show a minimum amount of external effects, that is the resultant vector force and the resultant vector moment. So assuming a point O, okay, we sum forces and gets us the resultant, and then we evaluate the moment of each of the forces about that point O, and it's going to give us a resultant moment. Okay. Now, if forces are concentric to a point, then as we learned earlier, it's the Wigner principle. So the moment is going to be the of the individual forces taken together is going to be the moment of the resultant. Okay, so yeah, these are the equations that summarize what I said. And again, we can have moments that are applied in other than separate from the forces. You have couple moments. They don't contribute to the first term sum of forces because their forces are equal and parallel. But if when we do include them, we add them as vectors. Okay, so you sum the external moments and then you evaluate the moment of the forces relative to that point. Again, moments can be anywhere. You can move them parallel to themselves. They are free vectors. Their effect upon the via the body upon the environment will be the same. In two-dimensional cases, so this becomes some force in the x direction, some force in the y direction, and moments are going to be all perpendicular to the xy plane. So moments will have the either positive or negative direction of the z-axis, and the the corresponding scalar equations to the three dimensionals. Most general one is this equation 418. Okay, so important points. Force is a sliding vector. Couple moment is a free vector. And if I move a force parallel to itself, then in order to create the same external effect, I need to include a moment. So yeah, there's an example here with traffic lights. So I have the two weights, and if I move them, add them, W1 plus W2, they are parallel. Show them here at the joining between the horizontal and the vertical mast. Then I need to introduce this moment, which really is going to be W1 times D1 plus W2 times D2. They're in the same direction and acting counterclockwise as shown here. Okay, so let's move forward. Again, hopefully we'll have enough time to do good amount of exercise. These are important concepts. So, coupled system is this section, rather further simplification of a force in coupled system. If you have forces that are intersecting at a point, again, you slide them along their line of action, and you're going to find the resultant. So about point O, where which they converge, there's no moment. So these are concurrent force systems. Now, if I have, these are no longer concurrent, so I can evaluate the resultant force, and then about some point O, it could be the center of the slab, and then the moment, sum of moments of the individual force about that same point O. And I can further, another equivalent system would be where I'm showing the resultant force offset from the point O by the amount D, such that this force is responsible for creating the resultant moment. So again, if the forces are concurrent, they don't generate the moment about their point of intersection. If they're not, then they generate the moment, and I can induce that moment by just offsetting the resultant the right amount. We've got the equivalent force moment system. And maximally simplified. If we have parallel forces, and many cases in practice of this type, so gravity uh, at the lab scale or planetary scale. So forces are parallel, the weight forces, although here one is down, two up. So um, yeah, we can evaluate the resultant of the force. We add them. Um, they have only z component in this case, and then we can evaluate the moment of these forces, three forces about an axis through O, or about point O, and then we can assume that the resultant force offset the right amount can be calculated such that this resultant force causes the moment that the individual forces uh, together are inducing upon the body. Okay. So yeah, a summary of what we learned. Again, it's a matter of simplifying a system of several forces with application you'll see at like distributed loads. Reduction to a wrench. Um, so if we these are forces that are parallel, we can have forces that are um, at some orientation that cause moments in several direction maybe. Anyway, so we can show the resultant of a moment and the resultant force and resultant moment as a two vectors. That is, moment and force are in alignment. That's called a wrench or screw. And so yeah, that will be the maximum simplification that you can reduce a system of multiple forces. Okay, and then there is a section we discussed parallel forces, so reduction of simplified distributed loads. Um, Again, this could be fluid pressure, air, water acting upon the rudder of a boat, or air pressure acting upon the wing of an aircraft, or some surface, control surface. Or could be distributed load, could be snow on an overhang or on a beam that is supported, or could be sand on a truck bed. Okay, so we want to get the equivalent force of these distributed forces evaluated, and assuming that they are given as smooth functions of time, then would just be a matter of, so again, this is force per unit length, force per millimeter per inch, and it's given as a function. This appears to be a parabolic distribution. So what would be the resultant force? That's really equal to the area of the surface, or it could be the volume. If this is given, you can have a distribution that varies both in the x and the other direction perpendicular to x. Is not labeled here, could be y. Anyway, so the way you get it is through or by integration. So we take a narrow portion of the beam of infinitesimally small dx, and we multiply by the distributed force, again, which is given as a analytical function. And the resultant force is going to be the integral that's shown here. So really it's the area under the curve, this curve. Now, where is that force acting? And anticipate that force, it's acting at the centroid of the figure formed by the distributed forces. Okay, so to get that, we need to get the location, find the location of the resultant. We need to evaluate the moment of the distributed force times dx, the little amount of area, times the arm of the force. So looking at this figure here, so we have the force acting per length dx is going to be w, which is function of x times dx, and they multiply by the distance from the axis. It'll be the axis perpendicular to x and to w coming towards us. Okay, so times, so it'll be this resultant force acting per unit length, or could be unit area, times the arm of the force. So the formula to go with is again the moment of the infinitesimally force divided by this integral, which is essentially the resultant. So that will give us the distance where the x overscore, where I need to concentrate all these forces in order to have the same effect upon the supports of the body. Okay. So yeah, if these are analytical functions, w of x, you can work with integrals. Otherwise, if they are simple figures like rectangle, triangles, even for parabolae, there are appendices in this book that gives us the centroid and areas. But sometimes we need to do integration. And there's chapter 9 where these are discussed again. Okay, so yeah, I guess this was the plenty of problems to solve. And again, the summary of the chapter, it's where we started. And with this, I stopped the recording. Thanks for watching.